Hello, buddy. My name is Christopher Blouin, and today I'm going to be walking you through my research with Dr. Larsen into computational analysis of light decay through atmospheric media. Okay, so to give a little bit of a background on this, essentially what we are trying to study here is how light's intensity decays as it traverses through air. Now, as light travels through air with particles, some of that light is redirected via the interaction with particles. Now, that total fraction of light that still travels forward is called the transmittance t, and it is related to a quantity we call optical depth, denoted as tau, with the relationship between the transmittance t and tau shown here in this bottom equation, and this is known as the Beer-Lambert-Boueger law. Now, one of the principal assumptions that the Beer-Lambert-Boueger law makes is that the particles that comprise medium are uncorrelated between one another. An example of an uncorrelated medium is shown in the image on the left here. Now notice how the particles look. For the most part, they appear evenly distributed. Now, it has been shown that most clouds and atmospheric particles have correlated positions, which can create clusters of particles. This clustering effect creates a clumpy media that can allow more light to escape through the gaps that the clumpy particles create. As a result, so-called clumpy media will not have a transmittance that would totally agree with the Beer-Lambert-Boueger law. Now, creating clumpy particles with a known degree of clumpiness and testing the resulting light transmission in real life is extremely hard. And so we use computational approaches to generate and simulate light transmission through these clumpy distributions. So to generate these clumpy distributions that I talked about previously, we use a matern particle generation algorithm that works as follows. First, a set number of parent particles are placed randomly within the volume, as you can see here modeled in 2D. Then a sphere of specified radius, referred to as the matern radius r, is drawn around those parent particles. Next, a number of particles drawn from a probability distribution with a specified mean value lambda is placed around each parent particle randomly within that matern radii r. Then the parent particles are removed and you're left with a clumpy distribution with known statistical structure. Now, moving this from 2D to 3D and vastly increasing the number of parent particles and daughter particles, we can get semi-realistic distributions for testing. Now, for our testing methodology coming up, we treat all particles as spheres and we treat light as individual photons traveling through the medium. Now, here is our key result. We simulated photon transmission by sending 125,000 photons through particle distributions, each having approximately 2 million particles. For each distribution, we counted how many photons ultimately went through our particle distribution and how many were scattered back towards the illumination source. The more particles that were scattered back, the higher the optical depth in the system. Because there are multiple layers of randomness here between photon entry locations and cluster locations, multiple simulations for each different type of distributions were conducted. This plot histograms the resulting backscatter with combinations of multiple simulations with the same statistical parameters grouped with the same color to get a sense of the simulation to simulation individual variability. Now we see the backscatter for the Poisson, which is perfectly random distribution particle placement, showing less backscatter than what we see from matern clusters of different radii, which is different than what we would have expected them to have. Now, here, we have the exact same plot, but expanded along the x-axis to show simulations with two much smaller matern radii, as you can see here in orange and yellow. And these give drastically different results. Now, the matern radii here are on the scale of millimeters, but that is still much larger than the individual particle sizes that are 25 micrometers in diameter. Now, this shows us two things. First, the matern radii and the severity of particle clustering do affect the optical depth as long as the clustering is intense enough. And second, it's likely that the effect due to clustering for larger matern radii shown on the previous slide are statistically indistinguishable from the Poisson simulation. For now, we can reconfirm what others have hypothesized in the literature. The effect on particle clustering on light transmission is minimal unless the particle clustering is rather extreme. So, to increase the statistical reliability of our results, we plan on furthering this work by increasing the number of photons in our simulations to assure that our values here are accurate. Next, we will explore alternative and more realistic models of particle clustering, including paying particular attention to making sure that the particles do not interpenetrate between one another. This effect, however, would probably only be noticeable with an extremely high number of photons. Now, with that, I'd like to say thank all of you for watching. Feel free to leave any questions or comments down below, and I'll be happy to answer all of them. Thank you.